this is a talk which motivates a little bit of geometry in the way we look at problems. So the basic idea is that once we get into notions like representing signals as Fourier series or using trigonometric functions, etc., we forget some inherent geometry in our problems. I'll give you a simple example to motivate this. So often when you look at anything which is periodic, so 0 to 2 pi or minus pi to pi, you are essentially doing this. You're writing things between 0 to 2 pi, right? So this is a real line. 0 to 2 pi is a subset of the real line. Does everybody agree with that? 0 to 2 pi is just a subset of the real line. Now, if I am translating this of an object which is coming from a circle, so this is maybe 0 and I go back here, I get to 2 pi, 0 to 2 pi. What is it that this line loses out in representing the circle? So just like when you go to a birthday party, you come back with a bag of gifts. So I've got something here which is not like a bag of gifts but something else. Okay, as you answer that, I'm going to explain things to you. What is it that we lose out? Is my question clear? I want to make sure. What is it that I lose out when I represent a circle on a line as 0 to 2 pi? Radius. Okay, let me not be concerned about my radius. I'm going to talk of unit radius. Periodicity. Can you be a little bit more specific? Yes, perfect. I mean, it's a circle and you can't. Let's look at something. On the circle, I'm going to mark 2 points, A and B. I'm going to mark the same points on the line. What's different? Yes, A and B are reasonably close points on the circle, but A and B don't look anywhere close to each other on the real line. Why is that? Because, yes. No, I'm not even talking of going from here to there or anything of that sort. Absolutely not. I'm just asking you a simple question. If I were representing this circle in terms of this interval here, A and B seem to be quite far apart. Do you agree with that statement? Do you agree with that statement? Yes. Whereas when I look at A and B on the circle, I would say if A and B was here, yes, they are far apart. But A and B are close to each other. Yes.
If we open the circle, we'll get the points farther. We'll get it at the same point if we make it.
Yeah, that's because I don't want to cut open the circle. I love circles. I don't like to cut them, cut them up. So the objective is this. So the objective of this introduction is this, that by doing so, you've lost the geometry of the circle. So how many people, I know many of you do autonomous system, robotics, quadrotors. Same problem goes. What is there? There's something called an orientation. There's something called an orientation matrix, which is a rotation matrix, right? And what is this rotation matrix? It's a 3 by 3. It's a 3 by 3 matrix. And what's so special? Everybody is flying drones and saying orientation of a drone. If a drone does this, let's say this is my drone, right? I want to image a player on a football field. I'm going down, there's a camera here. The camera is imaging the player. However, instead of going like this, if I went like this, what was wrong? My orientation is wrong, right? Position is okay. Position of my quad is okay. But instead of being like this, because my camera is pointing downwards, I'm going this way. So orientation is extremely important in autonomous vehicles. You cannot forget orientation. But there is something about orientation which is similar to this. And that is indeed, it's a non-Euclidean object. So non-Euclidean object. Where have you come across this? If you have heard it, can somebody give me some guesses to what is non-Euclidean? Parallel lines are not parallel, that's not true. If somebody gives me two parallel lines and tells me they are not parallel, I would not believe them. They are parallel. So here's my goodie number 2 from my bag. So that's a globe. You all familiar with a globe, right? So now I'm going to put this question. I have a point on the North Pole. I have a point on the South Pole. What's the shortest line from the North Pole to the South Pole? I'll have one here, but I could also have one here. I could also have one here. There are infinitely many shortest paths. To make it clear, there are infinitely many shortest paths from the North Pole to the South Pole. So now can you answer my previous question, which is, there is something strange going on here, because if I were given on this plane of this board, I were given 2 points, the only shortest path is this. This is not a shortest path, this is not a shortest path, this is not a shortest path. So obviously there is something different about the surface of this globe, right? It's giving me multiple short paths. Now this was the surface of the globe, but the same thing happens in the world of quadrotors too, if you look at the orientation matrix. So that's the theme of my talk today. And so goodie number 1 was, so what I wanted to demonstrate by the circle and the straight line example was an experiment I see in many engineering colleges when I go is a pendulum on a cart. Many of you would have seen that pendulum on a cart? No? Yes, okay. So let's forget the cart. Let's just look at the pendulum. So it's able to oscillate like this. It does this. If I were to pivot a pendulum here and look at this equilibrium and this equilibrium, what is the difference? Which this is stable. Why? Eigenvalues, I don't know what eigenvalues are. I just know the world in simple ways. So eigenvalues are way beyond me to understand. Gravity. Why gravity? Gravity acts even here, it acts here. Why should gravity? I mean, if you can be more specific about it. Yes. Perfect. Yes. That's a nice answer. So his answer is, if I perturb the pendulum in the downward equilibrium a little bit, it does, there's one thing wrong with your answer. I want you to reflect on it. He said it will come back to its original position, whereas if I did that here, it will just go away. It's not that it will come back to its original position, it will stay close to the original position. It's only if there's damping here, right? If the pivot had damping, then it will slowly decay and come back. Okay. So that is, okay. The other reason why I got this up was, if you designed a control law, so let's say you had a motor which was torquing this pendulum, right? And you wanted to stabilize it here, and you took an angle convention so that it was close to the upward equilibrium, but because of your angle convention and this strange philosophy that you applied, instead of doing a control law which goes like this, it does this way. Because in designing your control law, you have forgotten that the pendulum is evolving on a circle. So that's what it is. And let's keep this. Let me come to another problem. All of you have seen the parallel parking of a car in any place, right? What does parallel parking do? So you have a pedestrian curb here. You have a vehicle here. You have another vehicle here. Now you bring your car. You would like to park your car here, and your car is here. How many controls does a car have, a vehicle, a standard automobile? Anybody? How many controls? Like, even if you've not driven a car, you've sat next to somebody who's been driving a car. So how many controls do they have? They steer and they press the accelerator or the brake, right? So what does one causes motion like this? The other, if I were to look at the wheel of the car from top, it causes a steering, right? Those are essentially the two controls. Can a car's, I've taken one wheel, can it move like this? It does not move. So when I bring my car here and want to go here, my first reaction would be, no, I cannot do it, but I still do it. What enables me to do it? What enables me to park my car here? Have you would have at least observed what happens, right, when somebody parks? Yes. I'd like to have some other people answer as well. That would be nice. I'll definitely give you a chance. Somebody else would like to attempt an answer? Yes, please.
Sir, instead of moving the wheel, you can move the car itself. So you can rotate the car itself. So you can approach the path at a different angle and then correct your angle finally.
No. Somebody else? Okay. Oh, yourself, yeah, you wanted to take a...
So you move forward and then you take like a weird S-shaped trajectory. Like you move forward, then you put the car in reverse, and then you take an S-shaped trajectory like this.
Okay. What do I do? A simple thing, if I need to park.
Actually, we'll move, radius of curvature will help us. Means,
I don't know radius of curvature.
okay, I was
I
thinking-
just, I'm a very naive, uneducated person. I've been told you can steer. I've been told you can press the accelerator and brake. I don't know radius of curvature. I'll learn 10 years later. So how do I do it?
you take
Okay,
back.
you do, it's a simple maneuver, right? Let me do this. So here's one wheel. So I'm not drawing the whole car. What's the objective? The objective is, I think I'll not use green because I think it doesn't appear properly. So you want to do this. You want to bring it here. So what do? You first rotate, right? So then you are in this position, correct? Then what do? You reverse, right? Where do you get? You get somewhere here, correct? Then you steer. What happens then? You then you get into, let me say like this, right? Do you see that? Steer, drive, steer, drive. Then you are here. Oh, you don't want to move the whole car? Okay. I'm not going into so much of the nitty-gritties of the mechanism, as I want you to understand that there is something inherent in wheeled motion. I want you to understand that there is something inherent in wheeled motion which links to geometry, right? So does everybody see that? A sequence of steering, driving, achieved a parallel displacement. Now, if I told you that comes from the cross product, you'd not believe me. Say, I mean, why did you learn the cross product? In physics, where did you first encounter the cross product? Okay, let's forget the physics of cross products. What did a cross product do? It took two vectors. Okay, let's call two vectors x and another vector y. What did x cross y do? First and foremost, it gave you a vector, and that vector was perpendicular to xy. Doesn't that sound something like that? You had a steer and a drive, but then you went in a completely different direction than steer and a drive. So, the properties of a cross product would also manifest here, but the cross product is a very elementary notion of understanding such things. So, what's more, that's got something more involved, which I won't go into it. So now let me start my formal talk here. I've shown you a few experiments and mentioned a few things to you, but this is the outline of my lecture. So, oh yeah, I have two more goodies left, so we'll come to that when we come. Okay, 4 experiments and a disconnect. So the circle and this, right? We talked about this. So for those of you who heard of Michael Atiyah, he's one of the most leading mathematicians at Cambridge, right? So he has this statement to say. And the reason I put this statement is almost every other college I go to in India, mathematics is just impressing somebody with calculations. I mean, if you can do something very fast, sine squared cosine t divided by x squared plus e to the x, sir, मैंने 2 minutes में कर दिया ये problem. So that is mathematics, and you don't really look beyond that at all. So what this says is algebra is the offer made by the devil to the mathematician. The devil says, I'll give you this powerful machine. It will answer any question you like. All you need to do is to give me your soul, give up geometry, and you will have this marvelous machine. Okay. Now let's come to, we've seen a little bit of 2 and 3. We don't know what's 4, we don't know what's 1. We have seen a little bit of that. So now I'm going to pose another problem for you. How many people have thrown up a tennis racket? How many people have spun and thrown this racket up? Did you notice something very strange? If you note this, you'll notice the same thing holds for a quadrotor. There are mechanisms in the quadrotor which are emulated by this racket. So what have you noticed when you, so say, let's say I can spin the racket, right? I can spin the racket like this, I can throw it up with a spin. But I can also spin it like this. I can also spin it like this, and then, yeah, I can also spin it like this. I have 1, 2, 3 axes which I can spin, right? But there's something strange which goes on when you put a tennis racket up. So let's watch.
What you are looking at is known as the Janabekov effect, or the tennis.
Okay, what's happening there? Just watch it very carefully. This is on a spacecraft. He's opened a rivet, and the minute it comes out, it's spinning, but it flips. So it's spinning like this, then suddenly it flips. Just watch that.
Tennis racket theorem, or the intermediate axis theorem, but we'll get to that. Now you may have seen clips like this one before, but in this video I will provide the best intuitive explanation of how this effect works, or at least that's my goal. The bolt, he noticed something strange. The wing nut maintained its orientation for a short time, and then it flipped 180 degrees. And as he kept watching, it flipped back a few seconds later. And it continued flipping back and forth at regular intervals. This motion wasn't caused by forces or torques applied to the wing nut. There were none. And yet it kept flipping. It was a strange and counterintuitive phenomenon. And flip it in the air like this, it not only rotates the way you intend it to, it also makes a half turn around an axis that passes through its handle. So the side that was originally facing you will be facing away when you catch it. Now to understand this, we need to go through some basics. Like there are 3 ways to spin a tennis racket about its 3 principal axes. The first is about an axis that runs through the handle, like this. The second is the way we were spinning it before, with an axis that runs parallel to the head of the racket. And the third is about an axis that runs perpendicular to the head of the racket. Now it's easier to spin the racket around some of these axes than others. That is, you get more angular.
So that's a key point you have to listen to. He said it's easier to spin the racket about some of the axes than the others. And that's a very important feature when you recover spacecrafts which are rotating up in orbit. Say you want to get them back for some repairs, and you have to recover them and they are spinning in certain directions. So which is the direction which is a preferential spin, and in which direction can it lose? Can you lose control of the satellite? So let's watch this a little bit more.
Velocity for a given amount of torque. It's easiest to spin the racket around this first axis. It gets going really fast, and that is because the mass is distributed closer to this axis than to any of the others. We say its moment of inertia is the smallest when spinning in this orientation. Spinning about the third axis has the greatest moment of inertia, and so the racket gets spinning pretty slowly. And that's because this mass is distributed as far from this axis as possible. So this is the maximum moment of inertia axis. Now what you'll notice with spins about these axes is that they're stable. There's no rotation happening about any of the other axes.
So that's the other thing that he mentions. Spin about the largest and the smallest moment of inertia axis are stable spin axis. So your tennis racket would not go into some type of a weird motion. But the minute you spin it about the intermediate axis, then something strange happens.
When you try to rotate around the first or third axes. But rotating about the second axis, the intermediate axis, where the moment of inertia is in between the other two, well, that is where you get this half twist. And there's virtually nothing you can do to stop it.
Okay, there's a part on differential equations which I'm not coming to here because I did that in my first lecture, so let's skip this. And what you can understand with this tennis racket motion is you can actually understand it through geometry. Why is it that the tennis racket behaves like that? Why is it that the intermediate spin, you spin it through the intermediate axis and then it enters into a sort of weird motion? Why does that happen? So that can be figured out by drawing portraits of the motion of the tennis racket. So these are portraits of the motion of the tennis racket. So let me explain one of the things. So if you see this axis, so where do you think I got this figure from? What do those circles represent? I've got contours there. So I'll tell you something. So this is the angular momentum about the first axis, the second axis, and the third axis. So if you intersect momentum, draw the momentum sphere, that is, you can draw various values of momentum and draw a sphere, and you have a kinetic energy ellipsoid, you will get these curves, and these contours give you an idea of how the tennis racket evolves for different conditions. Let's say you are here. So this has so much of angular momentum in this direction and this direction and this direction. So let's learn a little bit more about angular momentum through cats. How many people have lifted a cat and allowed them to drop? Yes, lifted. What have you noticed? Or you hold a cat and let them go. They land always on their feet. Why do they do that? Could you do it? I mean, if I took you up and dropped you, even if you, would you land properly like them? Okay, so let's look at this.
For me, the perfect landing follows an excellent in-flight movie, a delicious meal, and a light nap. But for cats, the perfect landing follows some mind-blowing mid-air acrobatics. They're famous for their ability to land on their feet, which is something we need to work on.
Let your feet go first!
Cats' legs extend under their bodies, acting as natural shock absorbers. Ours aren't as effective. Whoa. But I think he knows that now. I bet that blew away the cobwebs. Is a falling cat's ability to always land on its feet myth, miracle, or a marvel of physics? Well, the law of conservation of angular momentum states that when a cat is falling, turning one part of its body means another part has to turn in the opposite direction. First, he orientates himself by turning his head, and then he arches his back.
So the entire analysis is that the whole cat skeletal system could be divided into three components: the front part, the hind part, and there's a spinal part. And so this is a very famous problem which has also been used extensively in the way astronauts reorient themselves in space. Because when you're reorienting yourself, you are conserving certain quantities and then moving your hands out or legs out, etc., so that you change orientation.
Next, he fully twists his front legs, whilst his rear turns in the opposite direction. To complete the turn, he twists his rear legs whilst his front turns in the opposite direction. Once again, he arches his back to reduce the force of impact.
Okay, so we spoke of the parallel parking problem, and we saw some weird things happening there, and you achieved sideways motion with a sequence of steering and driving motions, right? So let's perform a simple experiment. So you take a Cartesian frame. So this is your x, y and z, right? X, y, z. Okay, x, y, z, right? So let's say we are performing a motion. So think of this as some object. So you're performing, you want to look at the thumb, you are performing motion along the thumb, I mean perpendicular to the thumb. So here we are, we go this way, then along the thumb, up here, again perpendicular to the thumb, and I get back to the first position. So if you see, I was traveling on a plane like the board. Again, let me do this so that you need to get the other part. Here, perpendicular to the thumb, along the thumb, perpendicular to the thumb, down. What did you notice of the final position of my thumb? It seemed to be in the same position. It returned to the same position, right? There was no change. Does everybody see that? Now, I'm going to perform the experiment, but I'm going to imagine myself at the center of a sphere. I've been motivating geometry, right? So let me think I'm at the center of a sphere and I'm at the equator. So here's my same, think of this as your rigid body, quadrotor, some unit like that, right? I'm going perpendicular to the thumb. Okay? Everybody agrees I'm going perpendicular to the thumb because I'm on a sphere, right? You go this way. I go along the thumb. I go to the North Pole. Then I go perpendicular to the thumb. What happened? The thumb was like this. It became this way. It reoriented itself. But all along, I was traveling only along the thumb and perpendicular to the thumb. But when I traveled on a Euclidean surface, that's the plane, I achieved no change of orientation. But I traveled on a sphere, I had a change of orientation. So think of that as connecting to this problem once again. So the geometrical objects are a little bit more complex for me to explain, but think of it, it's because of the fact that you have circular motion of this type which comes in. Okay. So that you see the actual. Okay. So we've spoken of objects moving on non-Euclidean surfaces, but how do you describe motion of such objects? So what is it that we always do with something which is on a non-Euclidean surface is that we tend to bring it down to a Euclidean surface. So that works as follows. Maybe a simpler question would be, we all know the parts of the earth, look at maps on the earth. How do we actually get acquainted with a map of a certain region? It's on a sheet of paper, right? An atlas is on a sheet of paper. How do you think they converted something on a sphere, like such as this? How did they convert it to a plain page? You flip through the pages of an atlas. That's essentially this. What do you think they did? Yes, what they essentially do is they take patches. They take patches of this and map it to a plane. They take patches of this. But I won't be able to take a patch of the whole globe. I'd not be able to do that. So they have regions of the earth. So you're mapping a region of the earth to something which is a flat sheet. And that's precisely the way you work with systems which evolve like that, including your quadrotor. Your quadrotor is a system which is in a non-Euclidean space. We don't recognize it. We always use Euler angles, go ahead with Euler angles, and believe there's a singularity in an Euler angle and change Euler angles. So that doesn't happen. So let's see. Okay, I've put in a last section because one of the interns who works with me, first day she asked me what I'd like to see what are groups. So I wasn't sure how to answer that question. So I said there must be a simple explanation. So groups are again geometric objects. So how many people here have heard a mathematical object called a group? Okay, you people have, I've mentioned it to you, and no. Okay, when you added your numbers, column vectors, row vectors, okay, let me pose that question a different way. I just told you there's an element of a quadrotor called an orientation, which is a rotation matrix, R, right, which is a 3 by 3 matrix. What are the properties of that matrix? Is it just a 3 by 3 matrix? No, I'm asking you what are the properties of a rotation matrix? When will you call something is a rotation? Suppose I fix a coordinate axis to you. I put an x, y, z plane on you and you rotate. What happens? Yes, go ahead. Can you use the mic, please?
It's a transformation of a vector.
Perfect. It's a transformation of a vector. Yeah, but then what does the transformation have? So I have R. Let's say x is a vector, so x is a 3 by 1 vector. Perfect. So it's a transformation on a vector. Is it just any transformation on a vector? So let's say you have
It keeps the magnitude constant.
magnitude of
The vector.
perfect. What else does it do? So how do I express that? So you're saying magnitude of this is the same. Is that what you're saying? Is the magnitude of this?
Yeah.
So what does that immediately give you? If this equals this, what does it say about R?
Oh, the inverse into the transformation gives identity. I think that's what.
Something more?
The inverse of the transformation into the transformation.
No. You're confusing yourself. Just go the simple way. That should be true for any R. So what does it say about R transpose R? What does it say about R transpose R? It has to be identity, right? This can be true only if this is identity for all X, right? Right. Positive, definite, again you are using terms that I don't know. I just started with a 3 by 3 matrix and he gave a very intuitive way of speaking of a rotation. And I don't know positive definiteness, so we cannot meet on that, right? So this is R transpose R is identity. Yet there is a problem with this. What's the problem? He's perfectly right in vectors not changing length. If I have a vector on myself, I look at myself in the mirror, the vector, does it change length? Does the height of my face change length in a mirror? Is that a rotation? It is a rotation? It's not a rotation. Why is it not a rotation? I'm not moving the principal axis. Let's maybe keep things simple. Let's keep things simple. Let's not get. My question is, I look at myself in a mirror. I have a strand of hair. The length of the strand of hair in the mirror does not change, unless it's a convex mirror, concave mirror. Let's not forget. I'm talking of just your dressing mirror. Let's just talk of. Let's not complicate it with forces and rotating objects, etc. Let's keep it simple. When you look at yourself in a mirror, is it a rotation? That's all I'm asking you. What is the one aspect which changes? Okay, I'll give you a hint. I'll give you a hint. Yeah, further, very nice. Can you? Let's maybe not complicate it. She got the answer. Yeah, what is it? Yes, you almost got it.
Yeah, like your right becomes your left, so like it gets inverted.
Perfect. A right-handed coordinate system in a mirror becomes a left-handed coordinate system. It flips, right? You look at a right-handed coordinate system, everything else that he said is perfect. What you said was right. Length of vectors don't change, but a right-handed coordinate system which is reflected becomes a left-handed coordinate system, right? That's the big difference. So I'm going to catch you again. So R transpose R is identity. So how do I express this fact that I want to remove? Okay, why is this important? You have, let's say you have a quad. It's got a frame fixed. So this is a quad, it's got a frame fixed to it. This right-handed frame, whatever the quadrotor does, is going to remain a right-handed frame. It will not flip to a left-handed frame, right? You have to impose that condition when you study the quadrotor dynamics. Therefore, in addition to this, how do I impose that condition? Can somebody tell me? And Kavya here is given the right answer about the orientation, but what is the mathematical condition? Let me give you a hint. You should be able to get it after this hint. R transpose R. So I'm asking you for another condition. What does R transpose R equals I give you about the determinant of R? So Arohi, since you like Lie groups, and what does this tell you about R? R should be skew symmetric, not at all. Okay, I'll give you, let's say determinant of R is alpha. will determinant of R transpose be different from alpha? Is the determinant of a matrix and the determinant of its transpose the same or different?
It is the same.
Okay. So if this is true, what is this equation? If I take determinants on both sides, okay. So far okay? Very simple. Call this alpha. So you have alpha squared equals 1. How many solutions can it have? 1? I heard people say 1 solution. There are 2 solutions, right? Plus or minus 1. So if you have plus 1, it's a orientation matrix. If you have negative 1, it's a reflection. So you eliminate, when we got this condition, we impose this, and we impose one more condition called determinant R equals 1. So is that clear? So it's not a skew symmetric matrix. Skew symmetric matrices don't have that properly. Skew symmetric matrices are associated with angular velocity vectors, right? They are not associated with orientations. Okay. Okay. So let me quickly go through this. I have 10 minutes more. So plain vanilla real numbers, strings of real numbers, if you have arrays of real numbers, and then you impose conditions on real numbers as we did to rotations, right? Okay, so these are non-Euclidean surfaces. So the beginnings of group theory is in symmetries. You analyze symmetries of systems, and that's where group theory comes. And it's based on the third postulate of Euclidean geometry, that there are invariants when you move coordinate systems. And let's understand it in a very simple way. So if I asked you, what are the symmetries of an equilateral triangle I've shown here? In which ways can you move the equilateral triangle or do something to the equilateral triangle which keeps the equilateral triangle the same? It doesn't change at all. The first thing I'll tell you is, if you put an axis perpendicular to that and move it by how many degrees, will it remain the same? (120), 240, yes. 360, yes. What about if I do this? I have an equilateral triangle and I have a altitude here. Suppose I reflect it about that. That is, I have the altitude, I flip it about that. It's going to be the same, right? Okay. Yes? So I can do nothing. Okay, what am I arriving at? I'm going to arrive at the exact properties that describe a group by this. So I can rotate by 120, 240, 0. I can reflect about this, this and this. Now suppose I reflect, I rotate. Will the equilateral triangle still be the same? So I compose 2 operations. I reflect and I rotate. Will it still be the same? Or no? I reflect, rotate, reflect, reflect. Will it still be the same? I reflect, rotate, 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 reflect. Will it still be the same? Yes. you can compose these operations whichever way you like. The equilateral triangle will still be an equilateral triangle, right? So here are examples. So here is a table. So I have compositions of operations, right? So once I can calculate the result of any sequence of symmetry transformations as well as their inverse. And inverse is nothing. If I go 120 degrees, I get back 120 degrees, right? So that's okay. Let's forget this, and so let's come to the first set of properties. So I'm almost towards the end of my lecture. So from this basic idea, I come to the first set of properties of a group. And why do I emphasize a group? Because the rotation matrix I've been talking about in this lecture is a structure called a group. And if you want to motivate it from your column matrices or row matrices, it doesn't have the same property, because if you add two rotation matrices, you no longer get a rotation matrix. If you add two rotations, you don't get a rotation, and you have these three properties. So I'll quickly go through them. Just the left side is based on the equilateral triangle that you saw. Now this is an abstract set. It has a binary operation. It takes two elements of the set to give another element. There is an identity element. In the case of rotations, it's just the identity matrix, which has this property, and for every element of the group you have an inverse. The only three properties you need are these, and you have a lot of mathematical objects which obey these properties. So I think I'm almost to the end of my talk, and so this is done. Okay, this is the last but one slide on why we don't do mathematics the right way. Why are 80% or probably more people scared of advanced mathematics? Is precisely this, which was made by a famous mathematician of the 20th century, and you can take a look at that. And after that, okay, so this is, let me show you my students first. So this is about a year ago, going in front of, if some of you know this place in Mumbai, and so this is a set of them, and this is about a year or year and a half ago. And some of the other wild things in my life are governed by these people here and these things here. And I think with that, I have also given you a list of books. If you want to look at geometry more, this is a list of books. If you want to do something more in many of the areas concerning robotics, autonomous vehicles, quadrotors, you can probably start understanding basic facts. So that's about it. I'm done. You can